this is geometric distribution. So in this geometric distribution, our random variable x is defined as the number of the trial on which the first success occurs. Okay, so let's say you're doing some set of trials, so you're only concerned, so your random variable is essentially the number of the trial on which the first success occurs. Okay, so this distribution is modeled as, so for capital X is equal to small x, there must be a run of x minus 1 failures followed by a success, right? So let's say you are doing some, let's say, a simple coin toss, right? So and your success was getting ahead. Okay, so and so in the first 5 coin tosses you did not get ahead, right? But in the 6th coin toss you got the head, right? So that number 6 is the number that can be taken by your random variable x, which follows the geometric distribution. That is the number of the trial, right? The number of the trial. So because that was the 6th trial on which we got our first success, so that is the value our random variable will take, right? So there must be a run of x minus 1 failures followed by a success. So our probability of x is equal to x will be theta multiplied by 1 minus theta times x to the x minus 1. Okay, so let's try to understand this as well. So this is your geometric distribution. Okay, so there one more distribution that we'll cover. The other is Poisson, so that you'll get clarity on. So I'll just try to cover this a bit quickly. Yes, definitely. I'll share the notes. Okay, so so in the case of a geometrically distributed, so firstly, whenever you are writing the probability for probability function for any random variable, you need to understand what's the definition, right? So this is the number of the trial, right? It's not the number of trials, or number of the trial in which we get first success, right? We're not even concerned about the second success, we're just concerned about the first success. Okay, so this px is defined as theta times 1 minus theta x minus 1, where x can take value 1, 2, 3, etc. Okay. So I guess you guys should be able to see why this distribution looks like this, right? So we just need one success, only one success we need, and we need x minus 1 failures, right? So the probability of failure is 1 minus theta, so this will be multiplied x minus 1 times, so that's why we have the power x minus 1 here, and we just need one success, right? After x minus 1 failure, so the probability of getting one success is just theta, right? So this is what the probability distribution function for a geometric distribution, right? So remember, so earlier we here in the case of binomial, so if you have x, in fact, all right, so you can try to compare your binomial and geometric in this case, but of course in the case of binomial we're concerned about let's say x number of successes, but in the case of geometric we're just concerned about only one single success. Okay, so the probability distribution will be given by this case. So this term corresponds to all the x minus 1 failures, and this corresponds to the last success, or essentially the first success, right? Because after that you're satisfied, right? Because you have defined your random variable in that particular manner, right? So right, and let's see what is the mean or expected value for any such geometrically distributed random variable. So this is mu is equal to 1 by theta. So let's say for a coin toss, this theta is 0.5, right? So 1 by 0.5 will be 2, right? So you'll say that I'll need on average 2 trials to get a single head, right? And then that makes sense, right? So when you toss a coin, you'll get a tail, right? And on average, you'll say that, yeah, let's say even if on the first occasion I am getting a tail, and on the second occasion I'm highly expecting that it will be a head. Okay, so on average we can expect that, yeah, uh, 2 is the number of trial on which I'll get my first success or getting a head. Okay, and X can take values from 1, 2, 3. Right. Shubhal is saying that trying to shoot bullseye by archer until he gets the first hit. Okay, so all the n minus 1 attempts, they are failures, but the first is uh, the first hit is the first success, and that is what we're concerned with. And here also we need to think that, yeah, those are independently and identically distributed, right? All these trials, right? So when you're shooting, right, so of course you're assuming that the archer is not so there's no change in his concentration or focus. So as in the probability of success that is defined by theta, that does not get changed. Okay, so those are the only things that we keep in mind. But I think, yeah, Shubhal, I think this is a really nice example for a geometric distribution. This is our geometric distribution. So the mean, it makes a lot of sense, and your variance will be defined by 1 minus theta divided by theta squared. Okay, so you can calculate these values. So it's pretty trivial. So expectation of x, or what we also call as mu, so that can simply be calculated as x multiplied by theta 1 minus theta x minus 1. Okay, so you can take theta out and you can do this summation, and yeah, you'll come up with a value, right? So theta times 1 by theta squared, and this will be 1 by theta. Okay, so you can you can do this, and you'll be able to figure, yeah, so you can do this particular summation, and you'll find that, yeah, mu will be equal to 1 by theta, right? So that's the expected number of trials I need to do to have my first success. So in the case of coin toss, so it will be 1 by 0.5, that is 2. That means I need just 2 trials to get my first head. Okay, and sigma squared, again you can plug in to the formula and you will get this, right? So this is what the geometric distribution is. And the example, let's say a number of coin tosses required for getting a head, right? So the mean is 2 and the variance is 2 as well. Okay, and this is the probability distribution function. And maybe I think we have a geometric distribution here as well. Yeah, so this is the geometric distribution, and let's say p is 0.5. So one thing here, so here also this is a single parameter distribution. So here also there's only single parameters, as is theta, similar to what we have seen in the Bernoulli distribution. Okay, don't confuse it with the binomial. I know they also both start with B, they both have L, but do not get confused. Okay, so yeah, so here also, as you can see, so let's say we are rolling a die. Okay, and so this can be used to model the number of times a die must be rolled in order for a 6 to be observed. Okay, so let's say your p is really low, so 1 by 6 is maybe, let's say how much is, so maybe let's say 0.15 or 0.15, right? So or maybe let's say if I decrease the probability of getting a 6, maybe 0.1, right? So as you can see here, so maybe I'll just, yeah, so I hope you guys are able to see this, right? So it's sort of so if the probability of getting a 6 is 0.1, right? So I can get that, let's say only in the first trial itself, right? And then you have all these values. So just hang on. Okay. So let's say if I increase the probability to maybe let's say 0.9, right? So we'll get that in the first trial itself, right? So uh, right, so this is how the distribution looks like, and of course you can play around with p, that is your theta, and you can see your CDF for this particular geometrically distributed. And as you can see, so for uh, the numbers, in fact, so there is a very teeny tiny possibility. So maybe I'll just plus this, or maybe I'll just, right. So here, if I magnify this, right, so here you can see there very slight jump for 8. So at least you'll need, let's say, 8 trials to get a 6. Okay, so you can just explore and experiment around with this, and you'll get the idea of geometric distribution.